welcome back to our video series on probability. In this video, we're going to begin looking at inference. Now, the idea of inference involves combining probability and data together to make decisions. But there are two types of inference we're going to look at. In the first type of inference, we're going to look at estimation. So perhaps I wonder what the value of the population mean is. The other type is hypothesis testing. Perhaps I wonder if the value of pi is some value. Now, it's important to note estimation and hypothesis testing can be done on any parameter. With estimation, just suppose we want to create an estimate for mu, our population mean. And recall, the expected value of x bar is mu. Since we don't know mu, we can use x bar. The question is, though, how good is x bar as this estimate? Well, we need to recall the probability x bar equals mu is 0. X bar is simply a point estimate. It only estimates mu. It doesn't equal mu. We've got no idea if we're correct in using x bar as our estimate for mu. We would hope that we are very close. But as we said, we know that the probability x bar equals mu is 0. So what we'd like to do is create an interval that we hope will capture the true mean. And in doing so, we can be correct more often. But for our interval, we do have some properties. We'd like the interval to have the following. We would like for our interval to be as narrow as possible. The narrower our interval, the more accurate we believe that we are with our estimate in estimating the true parameter. We neither want to overestimate or underestimate our parameter. And we'd like the ability to specify how often our interval captures the true mean. So, steps for coming up with a confidence interval. The first step, we'd like to specify how often we wish to be correct, and this is what we're going to call our confidence level C. The next step, we need to know sigma at first. So, in this video, we're going to assume that our population standard deviation, sigma, is known. And so what we're going to have is the probability that mu is in between A and B equals some level of confidence. How can we come up with this interval? Well, let's recall the empirical rule. If you recall, 68% of our data lie within one standard deviation above and below the mean. 95% lie within two standard deviations above and below the mean. And 99.7% lie within three standard deviations above and below the mean. And we could look at this as an interval, but we're not always going to be exactly 1, 2, or 3 standard deviations above the mean. And so what we're going to say is we're going to create the probability that x bar minus mu over sigma over the square root of n is in between negative a and a. Well, why x bar minus mu over sigma over the square root of n? Remember, we're talking about creating an estimate for x bar. And since we're looking at x bar, we have to employ the central limit theorem. But the probability that x bar minus mu over sigma over the square root of n is in between negative a and a is going to be some confidence. Well, remember, x bar minus mu over sigma over the square root of n is just a z-score transformation using the central limit theorem. And so we're going to have a lower z value I'm going to call negative z star L, and an upper z value I'm going to call z star U. And so this is going to be in between negative z star L and z star U, and it's got some confidence. Well, if I multiply both sides by sigma over the square root of n, I get negative z star L times sigma over the square root of n is less than x bar minus mu is less than z star U times sigma over the square root of n with our confidence. And then if I add x bar to both sides, I get the probability x bar minus our critical z star value times sigma over the square root of n is less than mu is less than x bar plus our critical z value times sigma over the square root of n. And I get that set equal to some level of confidence. In other words, in order to create the confidence interval, I'm going to need x bar plus or minus my critical z star value times sigma over the square root of n. So how are we going to use this? Well, suppose we wish to determine the time it takes for students to walk or drive to work or school each day. Further, we will suppose the population is a previous Stats 543 class, and we wish to estimate the mean time, so we're looking for mu, our average commute time to this class. Well, we're going to take 3 samples. Suppose we have the following values. Now, I'm not going to read all these off. You can pause the video and look and jot down all these values. We're going to do this example in R. Now, if we find the mean of each of these samples, what we'll find is that x bar 1 equals 15.667. X bar 2 is 20.333, and x bar 3 is 16.833. Each of these are wrong. However, each of these are a point estimate. So we can calculate a confidence interval for the true mean, but we need to recall that sigma equals the sum of the xi minus mu quantity squared over n minus 1. And if I sum up these squared deviations, I get 1,784.556 divided by 35. I get 7.14054. But it's important to note in this sample, we have a known population standard deviation. And we'd like to set our confidence level at 97%. Since we're going to set our confidence level at 97%, we need to find our z-star value. And our z-star value happens to be negative 2.17. But why use a z-star? Well, we have known population standard deviation. And if we have known population standard deviation, we can use z. So what is the confidence interval for our first sample? Well, if I look at x bar 1 plus or minus my critical z value times sigma over the square root of n, that is 15.667 plus or minus 2.17 times 7.14054 over the square root of 12. And I get an interval with interval values of 11.19399 to 20.14001. If I look at the confidence interval for the second sample, again, x bar 2, 20.33 plus this entire thing, this 2.17 times 7.14054 over the square root of 12. This is my margin of error. My critical z-star value times sigma over the square root of n. That's my margin of error. And so 20.33 plus or minus the margin of error gives me 15.85699 to 24.80301. In my third confidence interval, my sample mean plus or minus my margin of error, 16.83 plus or minus the margin of error gives 12.35699 to 21.30301. So how do we interpret these? It's not just enough to give the values. You have to interpret these values. We're 97% confident the mean commute time for Stat 543 students is between 11.19399 minutes and 20.14001 minutes. This is for sample 1. Notice what we've done. We've stated how confident we were. We've stated what our parameter was, and we've stated the interval width. This is the interpretation. This is the answer to the problem. So we're going to look at how we would do this in R. And then in our next video, we're going to continue on with inference, but we're going to look at inference on proportions. So let's take a look at R. I've got each of my groups, group 1, group 2, and group 3, and I'm going to concatenate all of these into a whole group. So I've run these. I want to be 97% confident. Now, I also need to create the standard deviation for the entire group. That's my known standard deviation, 7.140539. N1, N2, and N3 are the length of the groups. In other words, that's how many are in each group. And in each group, there should be 12, and there are. X bar 1, the sample mean for group 1. X bar 2, the sample mean for group 2. X bar 3, the sample mean for group 3. And then my z-star value. Notice what I've done here. I've used the Q-norm function, but I've used 0.985. This is because, remember, I want 97% confidence between here and here. If I use 97% in my Q-norm, it's going to give me everything beneath. But if I've got 97% in here, that means that I've got 0.015 on this end and 0.015 on this end. So 97 plus 0.015 gives me 0.985. Okay, so in order to create my confidence intervals, I've called this CL1, that's x bar 1 minus z star times standard deviation of the group over the square root of n. So let me run my z star here. And then I've added, so here is x bar 1 minus the margin of error, x bar 2 plus the margin of error. And I have to interpret this. CL1, 11.19, CL2, 20.13. And so to interpret this, we're 97% confident mean commute time for Stat 543 students is in between. Here are my values, CL1 and CU1, where CL1 is confidence low for group 1 and CU1 is confidence up for group 1. In other words, the lower and the upper confidence level value. Here I'm going to do the same thing with CL2 and CU2. So this is just the lower and upper confidence values for my second group. If I run this, 15.86, 24.80, and then I'll do, again, we need to interpret this. We're 97% confident mean commute time for Stat 543 students is in between 15.86 and 24.80. And then I'll do the last confidence interval for my third group, and I'll interpret this, and we're 97% confident that the mean commute time for all Stat 543 students is in between 12.36 and 21.30. Now notice, some of these intervals overlap, and that's due to the point estimate. The margin of error stayed the same. And so wherever the point estimate was, x bar 1, recall, was 15.67, x bar 2, 20.33, and x bar 3, 16.83. Our margin of error has not changed. This is how much we missed by. Our point estimate, X bar 1, X bar 2, and X bar 3 are all incorrect. They do not equal the population mean. They are simply a point estimate for the population mean. And so we want to, again, create our confidence intervals so that we've got an estimate. Okay, that's it for this video. In the next video, we will look at creating confidence intervals for proportions. See you then.